Welcome everyone, my name is Ulrich. I'm assistant professor at Carleton University in Ottawa, Canada. I'm also the founding director of the Spacecraft Robotics and Control Laboratory. So I've been involved with spacecraft guidance, navigation, and control for the past 10 years or so. First as a graduate student at the Université de Sherbrooke in Sherbrooke, Quebec, Canada. Then as a Spacecraft GN&C Research Engineer for a company called NGC Aerospace, also in Sherbrooke, Canada. And I went back to school to earn my Ph.D. in Aerospace Engineering, this time at Carleton University, and then continued on as a Postdoctoral Associate at the MIT Space Systems Lab in Cambridge, Massachusetts. And now I'm back at Carleton University as a professor teaching spacecraft GN&C and doing research in that field as well. So first off, I want to provide some key concepts on spacecraft GN&C. So first of all, spacecraft GN&C is an acronym. It stands for Guidance, Navigation and Control. Some people also refer to it as the AOCS. So that's the Attitude, Orbit, Control System. And in a nutshell, that's just one of the spacecraft subsystems. So as you know, on a spacecraft you have different subsystems. For example, the electrical power subsystem that looks over providing and storing electrical energy to the spacecraft. There's also a thermal control system that looks at regulating the temperature throughout the spacecraft. And the GN&C system is just one of the subsystems again. What it does is that it accomplishes three main functions on board the spacecraft. So as the name implies, it does the navigation function, which is the function that answers the question, where am I? So that's the function that will locate the spacecraft in terms of position, velocity, but also in terms of attitude, the orientation, and the angular velocity of the spacecraft as well. Then there's a guidance function that will determine where to go next. So I'll talk about that in more details in the next couple of minutes. But essentially that just defines the desired states in terms of position, velocity, orientation, and angular rate as well. And finally, there's a control function that will make sure that the spacecraft applies the required forces and torques to make sure that it follows as closely as possible the trajectory as defined in the guidance function. So if you look at the GN&C software at a high level, it acts like the brain of the spacecraft. So it will interface with both the sensor hardware that will measure the current states of the spacecraft, and on the other hand, it will interface with the actuator hardware to make sure that the spacecraft applies the required forces and torques. So the navigation function is a function that answers the question, where am I currently? So that's a function that will provide the spacecraft with the current knowledge on its attitude, its angular velocity, its position, and its velocity. So it does that based on the various sensor measurements. Unfortunately, because sensor measurements are corrupted with sensor noise, drift, and biases, you do need to have a navigation filter that will smooth out the noise present in those measurements. But also because you may not have all the required sensors that will measure all the dynamical states on board the spacecraft. You may need to reconstruct some of the states that are not measured with the hardware. So that's why you need a navigation function on board. So typical navigation techniques that will smooth out the noise as well as reconstructing the missing information coming out from the sensors include sensor fusion, which is very useful in robotic applications namely, and stochastic filtering techniques such as Kalman filters, extended Kalman filters, and unscented Kalman filters. Next up is the guidance function that answers the question, where to go next. So that's a function which is closely tied to the different mission requirements, and in a nutshell, it just specifies the desired dynamical states, either in the form of a waypoint as function of time. So for example, I want the spacecraft to orient its payload in that direction in 10 minutes from now, or I want the velocity of the spacecraft to be this value in 20 minutes from now. So these are waypoints as function of time that sets the desired states for you to achieve. Another way to do it is by including what we call a trajectory generator that will smooth out the transition between the different waypoints. The main objective here is that instead of having discrete waypoints as function of time, you end up with a continuous trajectory for the controller to be able to track it in a smooth way. Otherwise, if you just tell your spacecraft, well, I want you to be 10 kilometers ahead, for example, for a rendezvous and docking scenario in 20 minutes, then that means that the controller will have to digest a large initial error in terms of position tracking errors between where it is currently and where you want to go. So the way to solve this problem is by feeding the controller with a continuous, smooth trajectory. So these are the two main approaches to the guidance function. Now that you've estimated the full dynamical state vector based on the navigation function, and that you know where you want to go, the next logical step is to calculate the error between the desired states and the estimated states to compute the trajectory tracking error between those two and feed the signal to the onboard controller that will then make sure that the required forces and torques will be applied by the different actuators on board the spacecraft to force the actual spacecraft to follow as closely as possible the desired trajectory. Or in other words, to minimize the tracking error between the desired states and the estimated states as much as possible. So that's a high-level block scheme diagram illustrating the interfaces between the GN&C onboard software and the actual spacecraft hardware. So as you can see, the control function interfaces with the actuator. So the control outputs, again, are the required forces and torques that the actuators will have to apply to change the dynamics or force the actual spacecraft to do whatever you want it to do. And on the other side, you have the actual sensor hardware that interface with the navigation function to then estimate the current states of the spacecraft. And then ultimately comparing these states to the desired ones coming out of the guidance function and closing the loop this way. So typically, people kind of break down the spacecraft GN&C system into two subsystems. First, there's the attitude GN&C, and then there's the orbit GN&C. So the attitude GN&C is also commonly referred to as the ADCS. That stands for Attitude Determination and Control System. So that's the onboard system that specifies through the guidance function, that estimates through the navigation function, and that controls through the control function the attitude states of the spacecraft. Again, when I say attitude states, I refer to as the orientation or the attitude, as well as the angular velocity, so how fast you want the spacecraft to rotate. And typical application examples that require the need of an attitude GN&C system is whenever you want to point the scientific instrument, which is also referred to as the payload, towards a specific target, say towards the sun, towards the Earth if you are trying to image the Earth for environmental purposes. Also, if you're trying to point your antenna in a nadir direction that's directly down towards the ground for communication purposes with a ground station. Or if you just want to orient the spacecraft in such a way that it has a given orientation with respect to the sun for thermal control purposes. So if you're trying to cool or to heat some components passively on board the spacecraft using the sun as a source of thermal energy. But also whenever you try to apply thrust maneuvers to accelerate or decelerate the spacecraft, you want to make sure that the thrusters are pointing exactly in the right direction. So these are all typical examples where you do need to have an active attitude GN&C system on board. On the other hand, you may need an onboard orbit guidance, navigation, and control system, also referred to as the Orbit Determination and Control System, or ODCS for short, also referred sometimes as simply the guidance and navigation system. So similarly to its attitude counterpart, the Orbit GN&C is responsible to specifying, estimating, and controlling the orbital states of the spacecraft. The orbital states here referred to as the inertial position and velocity, or the relative position velocity in the rendezvous and docking scenario, or simply the orbital elements. So typical examples of scenarios that require you to have an onboard orbit GN&C system is whenever you're trying to do orbit maintenance. So for example, the ISS operates at a pretty low altitude, so 400 kilometers of altitude, and therefore experiences drag effects, which decelerates the spacecraft. And in turn, this deceleration will decrease the altitude of the spacecraft over time. So if you want to maintain your spacecraft for a long period of time in orbit, you'll need to raise the altitude to compensate for drag effects. So this is an orbit maintenance control maneuver that's typically performed. Also, station keeping for geostationary satellites, it needs to be within a specified volume called a control box, if you will, to make sure that the spacecraft is always pointing at the right direction over the ground. And for relative motion control purposes, so whenever you're trying to have two vehicles docking together, you need to control the approach trajectory in a very tight manner. So that requires a lot of orbit GN&C computational work. So there's the question of where physically do you do the spacecraft GN&C system? Do you do it on board the spacecraft or do you do it on the ground? Back in the days, people were doing it on the ground and they were just uploading the commands to the satellites to be executed on board the spacecraft. But nowadays, with computing techniques, we'll look at doing things mostly autonomously on board the spacecraft. The first onboard computers were just analog logic computers that were hardwiring the sensors to the actuators directly. But again, nowadays with the advances in digital computation, we use digital computers to do things on board. So this way, by using a digital computer instead of analog logic, it allows you to have a lot more flexibility in terms of reconfiguring the whole GN&C software even when the spacecraft is actually on orbit. It allows you also to interface the computer with quite advanced sensors and actuators that are all digital nowadays. So these are the two main advantages of using onboard digital computation to implement the GN&C software. And that's the current trend. So within this context, really the key objective of this talk is to provide you with an overview of autonomous guidance, navigation, and control for spacecraft. And finally, I'll conclude with two quick examples of spacecraft attitude guidance and then a relative position control for formation flying purposes to put things into perspective. So I broke down this talk into three parts. Part one, I'll go over the attitude GN&C. Then in part two, I'll talk about orbit GN&C. And finally, I'll talk about the two application examples I've just described. All right, so attitude GN&C, as I mentioned earlier, is responsible ultimately to control the orientation of a spacecraft to make sure that it points itself with respect to another body or another reference frame in some prescribed manner. That other body you're trying to align the spacecraft with or relative with might be the Earth for an Earth imaging mission, the sun, if you're trying to study the sun, or some specific stars out there, such as what Hubble Space Telescope does, right? It's trying to align its telescope in some prescribed direction to study whatever stars out there. And again, as I touched on previously, the GN&C software, now this time the attitude GN&C software interfaces with both attitude sensors that measure the current attitude states, and as well with attitude actuators that will apply the required torques to make sure that the spacecraft reorient itself accordingly to the desired attitude states as provided by the attitude guidance function. So that's the typical spacecraft attitude GN&C block scheme diagram where you see again the interfaces between the attitude GN&C software and the actual spacecraft, or in that case the output of the attitude control function is the required torques to be applied by the attitude actuators on board the spacecraft, and where the attitude sensors are kind of measuring the current attitude and the current angular velocity of your spacecraft, feeding this back into the attitude navigation filters on board the attitude GN&C software. So let's first look at the attitude sensors and the attitude navigation filtering techniques, because these two are closely related. So depending on which sensors you have on board, you'll have to use different navigation techniques. So for small satellites, or back in the days, what people were mostly using are sun sensors that measure the orientation of the spacecraft with respect to the sun, as well as magnetometers that measure the orientation of the Earth's magnetic field, and gyroscopes that measure the current or the actual angular velocity of the satellite. And typically what people were doing with these kind of sensors was to use simple low-pass filters to smooth out the noise inherent to those sensor measurements, or use some deterministic attitude determination techniques widely known in the field such as the triad, the quest, or the Q method algorithms. I won't dive into these because that's beyond the scope of this talk. But these are well-known techniques that will simply estimate deterministically the attitude of the spacecraft by merging these different sensor measurements together. Nowadays, with the availability of digital star tracker that measure the current spacecraft attitude in inertial reference frame, we use those kind of measurements with extended common filter techniques to not only smooth out the noise inherent to the attitude measurements provided by the star trackers, but also to reconstruct the missing states, which is the angular velocity, which is not measured directly by the star trackers. As a brief overview, star trackers, they work by having an onboard catalog of pretty much all the stars out there, and by comparing what the camera is seeing with the onboard map of the stars, well, that's how the star tracker can figure out exactly the current spacecraft orientation with respect to the stars or with respect to the inertial reference frame, its equivalent. So again, the main advantage here is that you can reconstruct, as I said, the missing angular rate of your spacecraft, which is not directly measured, and that provides you with a highly accurate and autonomous attitude estimation solution. So that's the current trend in attitude sensor and navigation. So now that you know pretty much where you are currently in terms of orientation and angular velocity, you can then specify the desired orientation and angular rate so that ultimately you can compare the two and come up with a tracking control error to feed the attitude controller with. So in terms of attitude guidance, it's pretty simple. If you look at the desired pointing directions, again, it really depends on the mission requirements, but typically you want to orient your payload according to the mission requirements. So if you have a sun observation mission, you'll want to orient your payload towards the sun, or if you have an Earth observation mission, you'll want to have your cameras pointed at the ground. Or in the case of Hubble Space Telescope, you want your telescope to be pointing at distant stars or constellations. But at the same time, you have some requirements on solar arrays pointing. So you want your solar arrays to be pointed as much as possible towards the sun to maximize the energy generation, the electrical energy generation on board the spacecraft. And there's another stringent requirement for communication antenna pointing for obviously communication purposes between the satellite and ground station. So if you just look at these desired pointing directions, these are usually specified as waypoints as function of time, so discrete desired orientation as time goes by. But as I touched on earlier, it might be better to generate a smooth, continuous attitude profile to smooth out the transition between those desired waypoints. It has a couple of advantages doing it this way. First, it avoids saturating the actuators. So instead of saying, okay, all of a sudden I want you to reorient yourself by 180 degrees, well, instead of doing this, you specify a smooth trajectory. So you spoon feed the controller with small increments in terms of desired attitude as time goes by. And also allows you, by specifying a trajectory, to kind of shape this attitude profile in such a way that you have an optimal reconfiguration maneuver, either time optimal if you're trying to do a maneuver as fast as possible, or a torque optimal attitude profile, if you're trying to minimize the usage of your actuators as much as possible, then you define specifically an attitude profile or an attitude trajectory in such a way. Another use of desired attitude, smooth profiles or trajectories is whenever you reorient your satellite, you may want to avoid specific forbidden attitudes. So for example, if you have a very delicate optical instruments on board the spacecraft, you may not want to point it at the sun because that might damage this instrument. So while you're doing the reconfiguration maneuver, you make sure that the spacecraft does not at any time point its sensitive camera towards the sun. So all this can be done when you specify a smooth desired attitude profile or trajectory, as opposed to just discrete waypoints as time goes by. So once you know exactly where you are to the attitude navigation and you know where you want to go based on your attitude guidance function, you can now look at how do you control the satellite. Now there are different approaches to control the attitude of a spacecraft. I'll just briefly explain the most common ones. So first up, the spin stabilization is probably one of the earliest form of passive stabilization that was used for spacecraft attitude control. And the way it works is that it's pretty intuitive. You just spin a spacecraft along a given axis such that you orient the angular momentum vector of your rotating spacecraft in the desired direction of interest. So if you're only concerned of pointing, say, a camera towards the sun, then you point the angular momentum vector of your spinning satellite towards the sun by spinning it in this direction. The key advantages of doing that is that it provides stable inertial pointing about that particular angular momentum vector. And also it provides some rigidity against attitude perturbations that might affect the current attitude pointing. So by spinning the spacecraft faster, you'll get higher rigidity. So in a sense that the faster you spin the spacecraft, the more robust that pointing direction will be in terms of robustness against the external perturbations affecting the spacecraft. So back in the days, people were thinking that you could either spin the spacecraft along its major axis of inertia or along its minor axis of inertia. Both should provide you with a stable attitude motion. That was back in the days. And in fact, that was before the US launched its first satellite in space. That was the US Explorer 1 satellite. So if you look at the diagram here, the satellite was like a pen-shaped body. And the idea here was to spin the satellite about the long axis, so the minor axis of rotation. So they were trying to spin the satellite this way. If you imagine this being the satellite, they wanted to spin it along its minor axis of rotation this way, because they thought that was a stable rotational axis. Unfortunately, due to mechanical energy dissipation through these antennas, flexible antennas that you see on the diagram here, a major axis of rotation is not a stable axis of rotation anymore. And in fact, after a couple of hours of spinning the satellite about this axis, due to the mechanical energy dissipation, it ended up being in a flat spin about the major axis of rotation. And this is how they discovered that the only stable axis of rotation, passive axis of rotation of a satellite, is along its major axis of rotation. And this is referred to as a major axis rule. So that's how they discovered it. So by the failure of this US Explorer 1 satellite.